In this video, we're going to look at pattern recognition in order to factor certain quadratic expressions. So remember, a quadratic expression could be written as ax squared plus bx plus c. In the first set we're going to look at, we're going to let a just be 1, so it won't appear. So let's look at a couple of patterns and see how they could allow us to factor just very specific cases. So let's look at the pattern when we take x plus 1 and square it. And then we'll do x plus 2 and square it, and x plus 3 and square it. Each of these could be rewritten as the product of a binomial written twice. When we use a distributive property to evaluate each of these, we could see that the first one, it has to have 4 products. So the first would be x squared, second product would be x, third product would be x again, and the fourth product would be 1. For the second example, we would have x squared as our first product, we would have 2x as our second product, and then we would have 2x as our third product, and we would have 4 as the final product. Then for the last one, we'll have x squared, and then we would have 3x for the second product, 3x for the third product, and we would have 9 as the last product. Okay, so we're creating a pattern here. You'll notice that when you square the x as part of the first product, you always get x squared, and then we have the perfect squares 1, 4, 9, because the constant term in each of the binomials was 1, 2, and 3, respectively. So we get the squares of those numbers when we square the binomial. Now, what's most interesting, though, is what happens in the middle. In the first one, when we took the outer and inner terms of the product, we have x plus x. In the second one, we get 2x plus 2x. There's symmetry because we have the same factor twice. And then we have 3x and 3x. So in every case, we can sum those up, and we'll have a similar pattern. The middle terms will always combine, and in the first case, they will combine to give us a quantity of 2x. In the second case, let me just write out the x squared terms. In the second case, the middle terms would combine to give us 4x. In the third case, they would combine to give us 6x. And then we just get the square of the constant term on the end each time. So we have these expanded expressions that look like the general form of a quadratic equation, where we have a nice pattern. In general, if we had taken x plus a generic number, and I will call that capital B to distinguish it from lowercase b, and square it, the pattern would be that we always get x squared plus a middle term that is twice the b value times x plus the b value squared. So that's sort of a generic formula. Now, how can we apply this? Let's look at a couple of examples. If we started with a general form of a quadratic equation that looked like this, we could recognize it to be the expanded version of a binomial squared. So you'll notice that we always start it with by squaring a binomial. So the result of that is called a perfect square. So when we look at the example that I just wrote, we can recognize that it is, in fact, a perfect square. The characteristics of the perfect square are that the 25 could be represented as 5 squared, and sure enough, the 10 could have been represented as 2 times 5. But probably shouldn't put an x in there. We should probably just put a big dot here, so it's 2 times 5 for the middle term. So that is a giveaway that it is a perfect squared of x plus 5. Here's another example that would be a perfect square. Let's write x squared plus 14x plus 49. The last term clearly could be rewritten as 7 squared, and the 14, sure enough, is 2 times 7. So it checks out, and it could be rewritten as the binomial x plus 7 squared. So it's a perfect square. You can check by expanding x plus 7 if that doesn't make sense right away. Now, just of note, if you randomly write something like x squared plus 5x plus 9, this sort of fits the pattern because the 9 is a perfect squared. It's the perfect squared of 3. But the middle term, 5, does not equal 2 times 3. Therefore, this is not a perfect square. So the key is, if you have a first term that is just an x squared or a variable squared, and a last term that is a perfect square when you write it in descending order, the middle term has to be twice the square root of the last term in order for it to be a perfect square. Now let's keep on going. So in other words, if you just randomly write out quadratics, even if the last term is a perfect squared and we have a 1 in front of the squared variable, it's not likely to be a perfect square. It only works out sometimes, or later on we'll see that we can force it to happen when we study parabolas. So this technique will be important because we'll often force a perfect square into an equation. So let's look at a couple of other examples. Let's consider what would happen if we expanded the negatives of some of these. Okay. So let's consider what would happen if I had, instead of x plus 2 squared, let's consider if I had x minus 2 and square it. So that would be the same as x minus 2 times x minus 2. When we expand that, we'll get x squared minus 2x minus 2x. And then because you have a minus 2 times a minus 2 and negative 2 times negative 2, you get a positive 4. So note this time the middle terms are both negative. So when we combine it, we get something like x squared minus 4x plus 4. So what has changed is the middle term is now negative instead of positive. But both the first and last terms are positive, just like in the case of x, the quantity x plus 2 squared. So we can have perfect squares where we have where we're subtracting the constant instead of adding it. The key, though, will be that the middle term will still be twice the b value. So notice we had started with, although you'll have a minus twice the b value, because you'll have a negative term, I should say, with has a size that is twice the b value. So let's just consider a quick example. If I had x squared minus 10x plus 25, clearly it could fit the model of a perfect square. Let's check. 25 is clearly 5 squared, and 10 is 2 times 5, but because of the negative in front of the 10, this must be the square of x minus 5 instead of the square of x plus 5. So look at the sign of the middle term to determine whether you are adding or subtracting the constant of the perfect square. Now, continuing onward, we could have more complicated cases of perfect squares. So let me write a few of those down. Let's consider 3x plus 5 squared. So clearly, because we're squaring a binomial, the result should be a perfect squared, but let's see what happens. So we have 3x plus 5 times the quantity 3x plus 5. When we square this, the first term will end up being 9x squared. 3x times 5 will give me 15x. and then 5 times 3x will also give me 15x due to the symmetry, and then we will end up with plus 25 when we take the product of the last term. We have 15x twice, so obviously those are like each other and we can add them. So we end up with 9x squared plus, let me write in 30x plus 25. Let me write a second example worked out, and then let's look for the pattern. So if I have the quantity 5x minus 2 squared, get the quantity 5x minus 2 times the quantity 5x minus 2. This time we have a subtraction to look out for. So the first term in our expansion would be 25x squared. The second term would be minus 10x, as would the third term. And then the final term would be plus 4. So note, we have minus 10x and minus 10x, so that appears twice. So would this be equal to, this would simplify down to 25x squared minus, in this case, 20x plus 4. So let's consider what happens to the middle term in both of these cases. If I look at the 30, where could I get that from? Well, the first term is the square of 3x, and the last term is the square of 5. So if I were to take 3x times 5, I'd have 15x. So if I multiply it by 2 one more time, that would give me 30x, and that comes out from having the 15x plus the 15x. So those middle terms are the product of the square roots of the last two terms, or better yet, if we go back to the binomial, we have 3x and 5. So you get that middle term twice. So this is a perfect square. We know it has to be a perfect square because we started with a binomial and we squared it. So we have to get a result that's a perfect square. The pattern is that the middle term is twice the product of the first and last term in the binomial to make it a perfect square. Same thing is true here. In the second case, we know that the first term in the binomial was 5x. If we take twice 5x times the second term in the binomial, we'll just worry about its size, is 2. We would get 20x. So that's an indicator that we have a perfect square. So let's look at this in the reverse direction. Let's write out an example that would be a perfect square and determine what it is the perfect square of. So if I had 16x squared plus 24x plus 9, this will be a perfect squared. We're suspicious. Hopefully you realize that the first term would have to be 4x and the last term would have to be 3. So that when we square the 4x, we'll get our 16x squared, and when we square the 3, we'll get a 9. But what happens in the middle terms? We would have two terms in the middle that would each be 12x. So 2 times 12x does in fact give us the 24x that we have here. So 16x squared plus 24x plus 9 is the perfect square of the binomial 4x plus 3.